So here are some differentiation demos here. They are inside the gradient descent code base. So let me open this. Okay, so first we are going to do symbolic differentiation. We've already done this just now in another video, but let me just walk through this quickly. So let's say we have, so now my computer is running fast, so it's going okay. So we have this function 3x squared plus x1 squared plus 4x2 squared, and we can we're using the symbolic toolbox here, and let me run that. We're using the Jacobian function. The Jacobian is 6x1 plus 8x2, which is the gradient. We can also use individual partial derivatives to construct the gradient, which is the same thing. We can substitute some value for x1 and x2, in this case 3, 4, in the analytical expressions to compute the gradient, 18 and 32. Because it's analytical, it knows that it's exactly 18 and exactly 32 as opposed to arbitrary accuracy, right? At this point, at least. Of course, if there's like pi and so on, then we will have some finite precision there. Let's say, right, so I just converted that to pi. So here it says 18 pi, but then if you want to have decimal sort of expansion for that, you go double, and those are the, instead of 18 pi, we have 56 point blah 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 with finite precision, right? And then here we are going to do the central difference approximation of that. Because I changed the function, let me change the function here as well. 3 pi x1 square plus 4x2 square. And I'm saying that the accuracy with which I can evaluate this function is 10 to the minus 12. Probably it's more like 10 to the minus 15 or 16. And I'm using the central difference formula here. I can open this function. And you can read through this carefully, but all it's doing is, for if there are n input variables, it's looping through all input variables and then changing the nth input, the ith input variable by minus del and plus del, which is like minus h and plus h in our notes, and then evaluating the function using this function called feval. So if you give if you say I want to differentiate this input function, this feval allows you to call the input function at this point with any additional parameters, and then you do that for plus h and minus h and plus h. You take the difference and divide by 2h, and that's basically your partial derivative. And you do that for every input, and that's basically the central difference formula here. Looks like I wrote this a long time ago. Okay, so that's going to be the gradient of f, and let's actually see how accurate that is compared to this analytically evaluated and then numerically evaluated expression. Okay, so let me just run that. Okay, notice that you are accurate to about 7 or 8 decimal places, right? So it agrees to about 8 decimal places, and that's something we kind of expected. If we, I think this central difference formula uses the cube root of epsilon, or the accuracy of function evaluation, as the delta, and we expect roughly, once you use that, we expect the accuracy to be about epsilon power 2 over 3, which is about 10 power minus 15. Power 2 over 3 is going to be 10 power minus 10, but of course that's just meant to be rough order of magnitude. Here we have about, I don't know how many significant digits there, but maybe that's about 8 or 9 or 10. Okay, so it's pretty good. It's pretty fast. the central difference because it just evaluates the function a couple of times and approximates it. And it's probably good enough for most purposes. Um, in our lab, we do optimizations involving thousands of variables, and very often these kinds of finite difference approximations are good enough for optimizing variables with thousands of variables. But in general, if you can get better accuracy, that's always better for gradient evaluations. So that's where automatic differentiation comes about. So let's look at automatic differentiation. Um, so here's how it works, at least in MATLAB. Each computing paradigm will allow you to do automatic differentiation a different way if it has automatic differentiation. So I just have this function called Rosenbrock function, which is this function 100 x2 minus x1 square whole square minus 1 minus x1 whole square, some function of x1 and x2. We want to find the gradient, let's say, and we use the central difference formula here. Let's just see what the grad val is. It's this quantity, okay, whatever that is, that's the gradient. I actually just evaluated the gradient 5,000 times just to see how long it takes. Looks like evaluating the gradient 5,000 times takes 0.23 seconds. And this is using this function called tick and talk. If you put something within tick and talk, it will tell you how much time elapsed between tick and talk. But if you just evaluate a function once, and if the function takes a very small amount of time, tick and talk will not give you a reliable estimate of the time taken. So we just evaluated it 5,000 times over and over again to get a reasonable estimate of how long it took. Okay, so each evaluation, I suppose, took 0.23 by 5,000, like 10 power minus 5 seconds. Okay, so a very short amount of time. So that's using central difference formula, which is evaluating the function once before and once after, taking the difference and dividing by the difference between those 2 points at which you evaluated the function. Okay, now let's do automatic differentiation. To do automatic differentiation, you will need to tell MATLAB with respect to which parameters are you differentiating the function. Okay, so instead of so basically we are trying to differentiate this function Rosenbrock blah 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 with respect to x. By the way, the Rosenbrock function is just a function that is used a lot in optimization sort of examples, because it's a weird looking function which can sometimes be challenging for optimization algorithms. In any case, so we are trying to differentiate this Rosenbrock function with respect to x. So we just say x, this is the way you communicate to MATLAB, that x is initialized to minus 1 comma 2, and then we say we want to differentiate future functions with respect to x. We want you to pay attention to anything that depends on x, and we would like you to differentiate anything that depends on x with respect to x, I guess, or at least keep track of how things depend on x so that you can differentiate things in the future. So that's what DL array declares to MATLAB implicitly. Okay, and then instead of evaluating the function which is this original function Rosenbrock normal, we write a new function. Let me open that. A new function with the same input x, but the output is not only y, which is just exactly the same as before, but y and dy by dx. Okay, and x has already been declared to be something that can be differentiated with respect to, and then you just go, just say dy by dx equals dl gradient of y comma x. We are differentiating y with respect to x, finding the gradient of y with respect to x. That's just the function. You stick that in there. However complicated, however steps you might have, like you can have z equals, I don't know, y times x cube, blah, 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 etc. And then you can just go dz dx equals dl gradient z comma x, and then you can return dz dx as well if you want. So you can have how many ever variables here, you can have how many ever outputs here. I'm not going to do that, just leave that alone. But you can make this however complicated you want. Okay, and of course y need not be just like y equals function of x. You can have hundreds of lines, thousands of lines, millions of lines between the first line and then the very last line can be y equals blah. That depends on all the previous lines somehow, and this will still essentially keep track of all the dependencies, how the final line depends on the x value before, and differentiate with respect to all that. Okay, anyway, so dy by dx is returned, and that's it. I'm going to um, this is how you evaluate the function with the gradient in this manner. We evaluate it as dl f eval, and I suppose you go dl f eval comma x, f val comma grad val. You can look at okay. So yeah, so you can take a look at the syntax of that. I don't think the second output needs to be the gradient. It could be multiple function outputs, and then you can have other gradient-like outputs if you want. It's whatever you write within this function is what gets output. Okay. Anyway, so I'm also evaluating this 5,000 times just to be fair, just to see how long it takes. So let me run this part, and then let me run this part. Looks like it's actually taking a bit longer for whatever reason. Okay, it took much longer. It took 15 seconds instead of 0.22 seconds. But that might be because this is a very simple function. When you're calling these additional functions, there is a lot of setup time. But when this function is really complicated, one can imagine that automatic differentiation is actually faster rather than slower than these central difference or finite difference approximations. So maybe you'll see some of that in the homework problems. It's certainly going to be more accurate. Okay, so what's grad val? And it's actually gives you this super precise number as opposed to here. I guess my computer is slowing down now. Maybe this is also taking a while. I'm running this section now. Okay, so this also took a while. Grad val is actually it's only accurate to 8 decimal places. So instead of it being 396, it's 395.999998 or something like that. In any case, so that's what you get from the finite difference formula here. It says it's actually a DL array because we are overwriting a previously defined quantity, but this has just been evaluated using finite difference approximation, right? So if you just you can evaluate it just once. In any case, that's basically it for automatic differentiation. You define what you are trying to differentiate with respect to, write a function that takes advantage of this DL gradient thing. You just put in whatever you want to differentiate and then whatever you want to differentiate with respect to, and then have that as an output. And then when you actually call the function, you call it using DL eval of function name and then input. If there are other inputs here, comma something other inputs, you just stick them in there. They can be DL arrays or they need not be DL arrays. In fact, I'm demonstrating that here. So here we have the same function, but instead of having a single input x, which is x1 and x2, I have two inputs x1 and x2 explicitly, and then we are just returning the derivative with respect to x1 here. So I just define x1 as a DL array, x2 is just a regular number, and then we evaluate the function here and just return the derivative of y with respect to x1, and that's that. Okay, that's going to be 396 because that's what the derivative is. Okay, so that's automatic differentiation in MATLAB.